Hello, everyone. Welcome to a new lecture of our course on heterogeneous systems. Today, we continue talking about parallel programming and about GPU programming, and we are going to start a new series of lectures about important parallel patterns. In particular, today we start with the parallel reduction. But before we go into the details of the parallel reduction, let me very briefly remind you what we covered in the previous lecture. We were talking about GPU performance considerations. We discussed what are the main considerations to take into account when we are optimizing code for GPUs. Remember that one key performance consideration is memory coalescing, how we access global memory in order to utilize the bandwidth as good as possible. Remember that coalesced memory accesses that are the way of utilizing the bandwidth in the best way happen when consecutive threads access consecutive or nearby memory locations, or when all threads in a warp access data that resides in the same cache line or in several consecutive cache lines. Here in the slide, you can see a very good example of what is an uncoalesced or not coalesced memory access and a coalesced memory access. In the uncoalesced memory access, we have a stride between the addresses that are accessed by consecutive threads, while in the coalesced access, we have consecutive threads accessing consecutive memory locations. Remember as well that we talk about shared memory as a way of improving coalescing, because we can, for example, for these matrices, we can load tiles of these matrices into the shared memory. We can do these accesses to global memory in a coalesced manner, then write to the scratchpad or shared memory, and later access from the shared memory. And this way, we are avoiding the uncoalesced accesses to the global memory. Another important consideration is SIMD utilization. Remember that we talk about intra-warp divergence when we have threads in the same warp following different control flow paths. For example, here, imagine that we have two warps from 0 to 60 threads from 0 to 63, and we have even number threads doing something and odd number threads doing something different. What would happen here is that because the way threads in a GPU are in the same warp are executed in lockstep, and we use a mask in order to enable predication and enable control flow divergence, what will end up happening here is that we will have first all the even number threads executing the instructions in the if under the if statement, and then the rest of threads executing instructions after the else statement. So what we have is we are basically duplicating how we execute instructions here. What we could do is changing the way that we assign the computation to the different threads. And for example, we can have threads in the first warp, threads with a thread ID less than 32 doing this part of the computation, while others will be doing that part of the computation. And this way we'll have warp 1 executing the if part, while warp 2 will be executing the else part, and there is no intra-warp divergence. This SIMD utilization, or increasing the SIMD utilization, is important for the reduction operation, as we are going to see in a few slides. But before that, let me very briefly introduce what the reduction operation is. A reduction is an operation that reduces a set of values to a single value. It can be a sum, product, maximum, minimum. The important thing is that these operations have certain properties, the properties of reduction: associativity, commutativity, and an identity value, which is, for example, in the case of the addition or the sum, is 0. Reduction is a key primitive for parallel computing. It's using many different parallel programs. MapReduce programming model is a good example of that, but we can also find reductions in neural networks, for example, or in other machine learning workloads these days. Let's start with the sequential reduction. In a sequential reduction, what we are doing basically is executing a for loop that goes through a whole input array. If the array has n elements, we will need n iterations of this for loop. As you see, we start by initializing the sum to the identity value, but this sum is the accumulator where we are going to accumulate the final reduction result. We initialize it with the identity value, and then we go one by one over the elements of the array and accumulating and the sum accumulator. However, observe that there are many independent operations here, because in this parallel implementation, we can write a parallel implementation where we compute first multiple partial sums, and then we reduce them. And that's what we normally do in the classical way of parallelizing the reduction, which is a tree-based reduction. Imagine that we have an input array, A, with n elements. In the first iteration, what we are going to do is assigning different threads or different workers to pairs of elements in this array A. We perform the addition of these elements, and we store partial results in some temporary storage. In the next iteration, we will probably half of the workers or the threads will retire, and we continue doing the reduction of these partial results. We obtain new partial results that again store in the temporary storage, and we continue this way until we end up with a single value that is the reduction result. As you can see, in total here, we have log n iterations for an array of n elements, instead of doing the serial reduction where we have n iterations. If we map this tree-based reduction on a GPU, what we will normally do is, first of all, dividing the input array into different chunks that are assigned to different thread blocks, and then internally inside each thread block, we do the same, assigning parts of the chunk of the array to the different warps. This would be for warp 0, warp 1, and this in block 1. Now we are going to have threads in these warps performing the partial reductions or the partial sums that are going to result in some partial results that we need to continue reducing later. Here in the GPU, the temporary storage is typically going to be in the shared memory or scratchpad, or in the registers that each thread has been assigned. Another important thing to take into account is because threads or warps in the same thread block execute in lockstep, but different warps inside the same thread block do not execute at the same time simultaneously. They need to synchronize in some way. So we would use an intra-block synchronization or a sync thread that we already know from previous lectures. So we continue with the next iteration, and again, we need to use sync threads to synchronize and make sure that all the partial results are visible to all threads in the block in order to continue with the later iterations. Then we end up having a single partial result per thread block, and after that, we may need to use some sort of inter-block synchronization before we perform the final reduction of all these per block partial results. The way that we can do this inter-block synchronization, there are many different ways, or several different ways. The first of them is that we can move all these partial results to the CPU and then do the final reduction on the CPU. Another possibility is that we launch a new reduction kernel on the GPU, and we start from the beginning, performing all the iterations that we need to do until we end up having a single value that is the final reduction result. Or the last possibility is to use atomic operations in global memory. Basically, we would have one thread in each block, which would take this partial per block result and then accumulating it to some atomic variable in global memory using atomic operations. That could, any of these three possibilities would end up resulting in the final reduction result. Now, the question is, how do we map the computation internally inside each thread block and inside each warp? Imagine that this is our input array, and one possibility, because in the end, what we start doing is taking pairs of elements of the input array and calculating their sum. What we could do is assigning even number threads, thread 0, 2, 4, and so on, to consecutive elements. And they will start performing the reduction. In the first iteration, thread 0 adds element 0 and element 1, and it obtains one result. After that, we would synchronize, half of the threads retire, and then the remaining threads continue doing the reduction until we obtain the final result. The problem with this implementation that you can see, let's say that basic code for the tree-based reduction. You can see it here. The problem with this implementation is that it achieves low SIMD utilization. Why is that? Because if this one here is our input array and we assign the part of the array to different warps in this way, what will happen is that when a stride is equal 1 in the first iteration, only half of the threads work. Only those even number threads are working. And now observe that there is intra-warp divergence or low SIMD utilization because half of the threads are working, but the other half of the threads are not working. This turns even worse in the next iteration when stride is equal to, because now more threads in each warp retire, but there are still threads that keep working, keep active in all warps. And this is with the stride 4 and so on. So how can we avoid this warp underutilization? We can do a different mapping, a divergence-free mapping. In this case, we try to keep active threads that belong to the same warp. So instead of assigning even number threads to the different elements of the array to perform the partial reductions, what we do is that we assign consecutive threads to different elements in the array, and then we start performing the partial operations, the partial reductions. This could be iteration 1, in iteration 2, half of the threads retire, but observe that the threads that continue working are consecutive, and that means that they belong to the same warp, and so on and so forth. Now we end up having a program with higher SIMD utilization. Observe that the way that we are assigning the computation to threads and the way that we are going over the different stride values is different in a way that now when we start, we have all threads active in these 4 warps, then half of the threads retire, but all threads that keep working in the second iteration belong all to the same warp. So there is no underutilization inside each warp, and we continue this way. So warp utilization is maximized in this case. There is one more thing to take into account here. What happens when we are in the last warp? And when we are in the last warp, one thing that we can do in order to avoid to save some of these accesses to the shared memory, observe that this array of partial sums is in the shared memory. One thing that we can do is, for this last warp, is using some instructions that allow us to move data between or across the different threads of the same warp. These instructions are called warp shuffle, and we can use it for communication internally inside one warp. This way, we would be saving accesses, at least for this last warp, we would be saving accesses to this array in shared memory that is usually, it takes longer latency to access shared memory than accessing registers. So these warp shuffle instructions, they were introduced with the Kepler architecture a few years ago, and they are extremely useful because they enable threads to share data with other threads in the same warp. It's faster than using shared memory and then sync threads. That's why we are going to use it in the last warp of the parallel reduction, and then they have different variants. For example, the default one is shuffle sync, where we do a direct copy from the index lane. This is the source lane, and whatever thread that executes the shuffle sync will be reading one variable from one specific source lane, another thread in the same warp. There is also a shuffle up sync, where we are copying from a lane with a lower ID. There is the shuffle down sync, where we are copying from a higher ID. And there is this XOR using a bitwise XOR on the own lane ID. So now with warp shuffle, one thing that we could do is, first of all, performing reduction inside the same warp and communicating partial results across different threads in the warp warp using the warp shuffle instruction. And then we would continue was after we have a single value in each warp, we would do an intra-block synchronization with sync threads, and so on and so forth. And finally, remember, inter-block synchronization, either final reduction on the CPU, a new kernel launch, or atomic operations in global memory. So now let's take a look at the code using reduction with warp shuffle in this specific code. And there might be different ways of writing the reduction, but I'm going to give you an example here. In this specific kernel for the parallel reduction, we are going to use warp shuffle only in the last warp. So the very first thing that we do is declaring some array for temporary results, for partial results. In the shared memory is this input S, and first thing to do is to, for each thread, we go to the input array in the global memory. We take two elements from this input array, we perform the addition of these two, and then we store the result in the input S in the shared memory. After that, we synchronize, remember, because every time we update the shared memory and we want all threads in the warp, in the thread block, to see the same results, we need to use the sync thread, and then we start the reduction tree in shared memory. This code is exactly the same or very similar to the one we have seen in a previous slide that avoids the intra-warp divergence. This is a divergence-free reduction tree. So we perform several iterations here until we accumulate all the partial results input S in just one single element. After each of these iterations, we need to synchronize, and just after that, we just keep the last warp in the thread block, performing the reduction tree, but in this case with shuffle instruction. Just for the last 32 threads, we can do basically the same. It's a reduction tree again, but now we are using just this shuffle down sync in order to move partial results over different threads in the same warp. After we are done with that, we would have the leading thread, let's say thread 0 in this thread block, is storing the partial per block reduction into some array called partial sums in global memory. So this is the reduction with warp shuffle. In recent GPUs, since the compute capability 8.0, there is a new type of instruction that allows us to get rid of this tree using shuffle instructions and do it directly in hardware and in a more efficient manner. This is these are warp reducing intrinsics that, as I said, appeared with the compute capability 8.0, and we can just replace that final for loop with just this reduce at sync instruction. Now let me explain you very briefly one more optimization that we can apply here, and observe that it's something that we are going to do in the very beginning of the kernel. Observe as well that here, this is the, after this sync thread, we have the reduction tree in shared memory, which is basically what we have here in the original code. So reduction tree in shared memory, and after that, reduction with warp reduce or warp shuffle, as we have seen in the previous slides. So let's see what we can do before the reduction tree. What we can do is applying thread coarsening. And thread coarsening means basically that we are assigning to one individual thread the computation of multiple threads. So instead of launching as many thread blocks as we need to cover the entire input array, imagine an input array of tens or hundreds of millions of elements, we would need probably thousands or tens of thousands of thread blocks. Instead of using so many thread blocks, we can use a smaller number of thread blocks, but something that is enough to keep the entire GPU busy. And the threads in these thread blocks are going to perform the computation of those other threads of thread blocks that are not anymore launched. So imagine that now we are launching a reduced set of thread blocks that keeps the entire GPU busy, but not more than that. and we are assigning all the computation of the entire reduction of the whole array to only those thread blocks. One advantage of doing that is that we are going to save a lot of sync threads because we don't have so many thread blocks performing the tree-based reduction and using sync threads from time to time. So in the end, we can accelerate the performance. We still need to use an array in shell memory, but now what we do is that for each individual thread, we have a global thread index. Observe that we calculated using the block dimensions, the block index, and the thread index inside the same block. And now we also use the total number of threads, that is the grid dimension times the block dimension. So the total number of thread blocks times the number of threads per thread blocks. So now this grid size contains the total number of threads that we are using in our program. For each thread, we have a local or per thread sum that we initialize to the identity value, 0 in the case of the addition. And then we have this while loop, it could also be a for loop, where all threads go to the input array, fetch one element from the input array, and accumulate in their own local sum. After that, we update the index by adding the total number of threads. So if one thread read this element now, it will go somewhere later after all threads of the entire grid. The good thing of doing this is that, as you see, all threads work in an independent manner, in an embarrassingly parallel manner, and there is no need to synchronize across threads. We would only need to synchronize after we have gone over the entire input array. We have calculated all these local sums, and then each thread writes the local sum into the shared memory, and they synchronize using sync threads. And next, we can start with the reduction tree in shared memory as we did earlier. So as you see, there are many different combinations that we can use, different instructions like warp reduce, warp shuffle, different techniques like the tree-based reduction, or like the thread coarsening to compute partial sums in each individual thread. There is a huge search space for the parallel reduction, and that's something that different libraries and compilers as well explore automatically in order to find the best version for different architectures. That's something that we did in a recent paper where we compare up to 85 different versions of the parallel reduction. This is all for now. If you want to learn more about the parallel reduction, I recommend you to take a look at Chapter 6 and Chapter 10 in the book Programming Massively Parallel Processors, and for sure the longer lecture. You can find the link at the bottom of the slide where we give a few more details about the parallel reduction and also more details about the shuffle operations as well. So this is all for today. Thank you very much for your attention. I hope you found the lecture interesting, and I hope to see you as well in the next lecture.